All right, now let's talk about functions. We begin with a definition. A function. A function is a collection of ordered pairs. Which no two distinct pairs have the same first entry. That doesn't seem particularly complicated of a concept. It's a collection of ordered pairs. So I could start writing ordered pairs like this. I could say 1, 5. I could say 2, 7. I could say 3, 15. And I could say 4, 81. And this is a collection of ordered pairs. Notice that in this collection of ordered pairs, the first entry, meaning what we usually call the x value, but it doesn't have to be x. It can be, you can say a and b. The first entry, in order to avoid having to worry about whether we're calling it x or y or z or q or anything else, we say the first entry. Okay. Notice that all of these first entries are distinct. They're all different. We don't ever reuse the same first entry. So this right here, this is a function. Let's say I had a collection of ordered pairs that look like this: 1, 5, 2, 7, 3, 24, and 2, 81. This would not be considered a function because here you have two distinct ordered pairs. They're different. They're two different ordered pairs, but they do have the same first entry. This 2 versus this 2 right here. So because these are the same, then even though this is a collection of ordered pairs, this is not a function. Okay. Let's say something like this: 1, 5, 2, 5, 3, 5, 4, 5. That would be considered a function because even though the second entries are all the same, that's okay. The definition of a function only requires the first entries to be different. So here, the first entries are all different. 1, 2, 3, 4. These might all still be the same, but that doesn't matter. That's not required of a function. They can be different, but they don't have to be. So this is still considered a function. Okay? Now you might note one word in here, the word distinct pairs. This is made important with an example like this. Let's say I have 1, 5, 2, 7, 3, 15, and 2, 7. Now at first glance you say, okay, well that's not a function because here I have two ordered pairs, and they have the same first entry. But notice they also have the same second entry, which means that even though it's written twice, this is not a different point. These are not distinct. These are not different. It's almost as if I accidentally just wrote the same point twice. Something like this is made clear when we look at the definition and read the word distinct. The word distinct tells us that if you ever have a copy of a point, not just part of the coordinates, but exactly the same, one of these is just a repetition and should just be ignored. So here, the remaining ones, the ones that are distinct, the ones that are not copies of each other, these all have the same first entry. So then this is still considered a function. So if ever you have a point that differs, they're not the same, but they do have the same first entry, that's not a function. But if they don't differ, if you just happen to have two exactly the same copy, then this is considered a function. Just like that. Now at this point you think, okay, well that's nice. It's easy enough to understand. I have ordered pairs and the first number has to be different. But what does that have to do with anything? We're talking about algebra. We're talking about graphs. We're talking about, well, not this. What does this have to do with the kind of math that we've been studying? Well, a function is just this. There's nothing else to it than just this. It's a collection of ordered pairs where no two distinct ordered pairs have the same first entry. However, you can interpret a function a different way so that even though it's still defined the same way, you can get a little more meaning from it and you can get a little bit more use out of it. So before we get into talking about functions in that way, let's go ahead and give the same definition illustrated a slightly different way, just to get a little bit more of a feel as to what we really mean by a function. Because yes, it's a collection of ordered pairs where no two distinct pairs have the same first entry, but somehow that's a little vague. I mean, we do have the definition, there's nothing vague about it, but still, it seems like something's missing. So I'm going to go ahead and give this exact same example of a function, again, and this very top one, but I'm going to give it a slightly different way. Let me write down all of my first entries. 1, 2, 3, 4. And I'm going to go ahead and put them in, put a circle around them, or an oval, not because it's important, just because I want to separate these from what I'm about to write over here. I'm going to go ahead and write down the second entries. 5, 7, 15, 81. 5, 7, 15, 81. And I'm going to go ahead and put a circle around these. I don't want to mix them. I wanted to keep all my first entries separate from my second one. That's the only reason I have these ovals here. Okay, so now let's go ahead and pair them. And you say, well, I thought you wanted to keep them separate. Well, I do, but I still want to be able to have this information. I still want to know that the number 1 from my first entry should be paired with the number 5 from my second entry. So the way I'm going to do that is I'm going to associate them with a little arrow. I'm going to say, okay, look, these two are tied together somehow. There's some reason why this number and this number belong together. So I'm going to go ahead and put a little arrow here to say, okay, if I have this first entry, that's going to give me this second entry. 2 and 7 are paired together, so I'll illustrate that with an arrow. And there, and there. So this shows the same information that we had up here. We show that we have every first entry is tied to some second entry, and here we have them all together. Okay? So now you might ask, okay, so where is the function? I mean, a function is a collection of ordered pairs. Or okay, here you've written it a different way. So what's the function? Is it these numbers right here? Or was it these numbers over here? Neither. The function is this. It's the pairing. It's the relationship. So here, these numbers are not the function, and neither are these numbers, and neither are all the numbers put together. The function should be thought of as the relationship of this number is tied to this number. This number is tied to this one's tied to this one, and this one's tied to this one. This is your function. Let's consider this next one over here. Let me write down all my x values together. 1, 2, 3, 4. I'm going to go ahead and put a big circle around them, a big oval around them. And then the second entries, those are all the number 5, so I'm just going to write the number 5. And just to keep everything consistent, I'm going to put a circle around that just so that it matches this previous illustration. All right, well, same thing. This 1 is associated to that 5. This x value is associated to that y value. This first entry is associated to that second entry. This first one is associated to that second one. And this first one is associated to that second one. And again, the function is not these numbers, and it's not this number, and it's not the numbers 1, 2, 3, 4, 5. You can tell I work very hard to come up with examples, right? 1, 2, 3, 4, 5. It's this. The function is the relationship between these sets of numbers. Okay, so what? A function is arrows? So what's not a function then? Well, look at this one right here. Let's say I have all my first entries written down. 1, 2, 3, 2. Okay, well, just like before, when the number 5 repeats, we didn't write it over and over again. We just wrote it once. Same thing here. Let me just write 1, 2, 3, because here this 2 repeats. So all my x values are 1, 2, 3. All my y values are going to be 5, 7, 24, and 81. 5, 7, 24, and 81. And if I take all my first entries and all my second entries, and I copy all of this information, I'm going to have relationships between these numbers and these numbers over here. So 1 and 5 are somehow tied together, 2 and 7, 3 and 24, but then also 2 and 81. Okay. This is not a function. You say, well, why not? That kind of looks the same as this, right? You have these numbers tied to those numbers. Same thing over here. What makes this one different? All right. Let's say I asked you, looking at this function right here, if I told you, my first entry is the number 2, and I asked you, what's my second entry supposed to be? Well, you would say 7. And that's the only answer you could give. There is only one second entry tied to this first entry. All right? Let's say I asked you for this function. Let's say my first entry is the number 4. What's your second entry? Well, it's got to be the number 5. Did you have a choice about that? Well, no, you didn't. There's no choice here. There's a single second entry that has to be associated to this first entry. There's no other option. There's one and only one correct answer. Over here, if I say, what is the second entry if my first entry is the number 1? Well, it's got to be the number 5. But if I ask you, if my first entry is the number 2, what's my second entry? Notice that you're not sure. It could be 7, or it could be 81. And you have a choice on that, right? It's unclear which one is the correct one. So if I tell you, okay, I know for a fact that my x value is 2. What's my y value? Your answer is, I'm not sure. That doesn't ever happen over here. If I tell you my x value is 1, you can say for certain that your y value is 5. If x is 2, y is 7. If x is 3, y is 15. If x is 4, y is 81. Same thing for all of these. If x is 1, y is 5. If x is 2, y is 5. If x is 3, y is 5. If x is 4, y is 5. But in this scenario, you have x is 2, and you are unclear as to which is the correct y value, because it could be either one. This is not a function, as we saw previously, and this is the reason why. Because one of your x values is associated to multiple y values. Or in other words, if I tell you x is 2, you still don't know what y is. So, even though the definition of a function is this, a function is a collection of ordered pairs in which no two distinct ordered pairs have the same first entry, one way you could think about a function is, it is a, and again, this is not a formal definition, this is just a way of thinking about it. It is a deterministic relationship. Meaning, once I know what x is, that automatically determines what y is. There's no guesswork, there's no choice. It is the one and only possible answer. That is a function. A function is a deterministic relationship. Over here, it's not fully deterministic. If x is 1, you know for a fact y is 5. But if x is 2, we're not sure. And that's what prevents this from being a function. Okay, so at this point, we say, all right, now we have a different way of thinking about a function. We have the formal definition, and we have an informal intuition. We have an informal way of thinking about it. But still, what does it have to do with the way we normally talk about math in these classes? Right? This isn't algebra or even arithmetic. There's no graphs here. Nothing that looks like a tradition, like math in a traditional way. Well, let's go back to the definition. A function is a collection of ordered pairs which, ordered pairs. When do we see ordered pairs? Ordered pairs are the solutions to equations of two variables, and they are often expressed as a graph. So let's consider this one more time, the same function, and maybe not a function. Let's go ahead and consider these from a third point of view. Let's talk about them as a graph. So let's say I have just this function here. and I'm going to express it in a graph. All right, so if x is equal to 1, 2, 3, 4, 5, like this. If x is equal to 1, I know y is equal to 5. So let's say that's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. And now I wish I hadn't chosen such large numbers. But oh well. Here, if x is equal to 1, y is equal to 5. If x is equal to 2, y is equal to 7. So just slightly higher than that. If x is equal to 3, y is equal to 15. Right there. And if x is equal to 4, y is equal to 81. So way up there. Okay, so I've got 1, 2, 3, 4 points that I've plotted. I'm not going to connect the dots here. There's no other ordered pairs besides those 4. So it's not like I'm connecting the dots or anything. It's just those 4 points. Okay, so now let's compare this to our not a function. All right. See if I can give myself a little bit more room here. Let's see, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. All right. When x is equal to 1, we have y is equal to 5. So right there. When x is equal to the number 3, y is equal to 81. All right. Let's see here. Oh, sorry, y is equal to 24. 1, 15, 20, 24, right about there. But now notice, when x is equal to 2, you have two different y values. You have 2, 7 is one of your points. So let me label that one. That one's 2, 7. And you also have 2, 81 up here. Whenever you have something that's not a function, graphically, the way it's going to look is you're going to have 2 points that have the same x value. Well, sure, that's what it means to not be a function, right? You have 2 distinct ordered pairs, 2 different points on the plane, and they have the same first entry. Well, if they have the same first entry, the same x value, that means they're going to be stacked right on top of each other. One will be higher, one will be lower, depending on the y value, but since they have the same x value, they're going to be right on top of each other. This is called the vertical line test for a function. If ever you have a collection of points, ordered pairs that have been graphed, if every vertical line that you draw crosses through no more than 1 point, then that must be a function. But if you have any vertical lines, all it takes is 1, if you have any vertical lines that cross through 2 points on your graph, then that is not a function. All right, so let's go ahead and state that over here. This is not a definition exactly. This is a test. It's a way of testing a property of a, in this case, of a function, or, well, of a relation. It won't necessarily be a function every time. So let's see here. This is called the vertical line test. And it states, a graph represents a function if, actually I should say a function in the plane, in the xy plane. The reason that distinction is made is not because of anything that we're going to talk about, but anyone who takes any math classes higher than this, you are going to talk about planes other than the xy plane. You'll talk about the polar plane, which is different from the rectangular plane. It's not something we get into in this class, but the distinction does need to be made because, well, if anyone goes into those classes, eventually this test doesn't really mean the same thing anymore. So here we make the distinction. A graph represents a function in the xy plane. If you're in other planes, that doesn't work anymore. Specifically in the plane, in the xy plane. If, and only if, so if and only if means this is the only time it happens. All right? It can't happen any other time. A graph represents a function in the xy plane if and only if every vertical line in the plane crosses the graph no more than once. We don't say once, we say no more than once, because it's possible it doesn't cross it at all. No more than once. Okay. So for example, or for examples, several of them. Let's say I have this curve here. And that little arrow just means it keeps on going forever. You know? Here, it doesn't matter what vertical line I draw on this plane. It will only cross the graph no more than once. Right? It never crosses twice or 3 times or 4 times. Here, this vertical line only crosses once, and that one only crosses once, and that one, and that one. All of them, they cross only once. Now, when we say no more than once, that means if it doesn't cross at all, that's okay. For example, look at this graph. Here, this one doesn't keep going. It just starts right there. It doesn't keep going in the other direction. Here, if I start drawing vertical lines, they all cross no more than once. Right? Here, you cross once and once. Each of these vertical lines only crosses once. Notice these vertical lines don't cross at all. They never cross. But still, not ever crossing is still no more than 1. It's not 2 or 3 or 4. So every vertical line either doesn't cross or crosses once. That's another way to say it. So what does it look like if it's not a function? All right, well, this is, there's a circle. Here, there's a vertical line that crosses more than once. All it takes is one vertical line to do this. If you can find other ones, okay, that's fine. But all it takes is one. Here, I found one vertical line which crosses the graph more than once, which means if you have more lines, well, that's fine, but you need only one. So here, this is a function. This is the graph of a function, but this is not the graph of a function. So go ahead and give that a try. Consider the following 3 graphs and go ahead and label them. Are they a function or are they not? Okay. So these are all actual graphs. You don't see all of them in this course. Some of them are from more advanced courses, but they're all they're all graphs of known equations. Let's go ahead and consider the graph of a cubic. Let's go ahead and consider the graph of an involute. And let's go ahead and consider the graph of a cardioid. All right. Take a moment and pause the video if you need to. Go ahead and label these. They're either the graph of a function or they're not the graph of a function. Once you have your result, go ahead and unpause and we'll confirm it together. All right, so this first one is in fact the graph of a function because every vertical line that you can draw in the plane will cross no more than once. If there are some that don't cross, that's fine, but they shouldn't cross more than once. So yes, this one is the graph of a function. This one here, same thing. Every vertical line crosses no more than once. Now, if you find even one that crosses multiple times, then that's it, you're done. But here, no matter how hard I try, I still can't find any that cross more than one time. So yes, this is still a function. This one is certainly not a function because right away I see this line right here, the y-axis. It crosses twice, once here and once down here. Now, are there other lines that cross more than once? Sure, I can find others. Look, there's one right there, and there's one right there. Does every line cross more than once? No. For example, that line only crossed once. And in fact, this line over here doesn't cross at all. But none of those matter. As long as you can find even one that crosses multiple times, this can no longer be considered the graph of a function. Now, once we have this notion of a vertical line test to help us distinguish a function from not a function, when we look at a graph, the natural question now is to say, well, where are these graphs coming from? Well, they're coming from equations. After all, whenever we form a graph, generally what we're doing is we're graphing the solutions to an equation in two variables. Right? So you might say, okay, well then an equation is a function? Well, not really, because after all, by definition, this is a function. It's a collection of ordered pairs. But what we can say is that an equation can make a function. The way that it's usually stated is it generates a function. So consider the following example. Consider the equation 2x minus 5y equals to 15. All right. Here we can graph this equation, and we can do so either by finding individual points and plotting and connecting the dots, or we can write this in the slope-intercept form, y equals mx plus b, and graph that way. It doesn't really make any difference which way we go about it. So here, I think I'll just go ahead and plot 2 points. Here I can say if x is equal to 0, if I set x equal to 0, well then 2 times 0 is 0, and that just leaves me a minus 5y is equal to 15. If I then divide both sides by negative 5, a positive divided by a negative is a negative, 15 divided by 5 is 3. So this is one solution to this equation, 0 for my x value, and negative 3 for my y value, 0, negative 3. If I then set, let's say 5 equals to, let's say y equals to 5, let's do x equals to 5. Let's go ahead and set x equals to 5. Well, then that'll give us 2 times 5 is 10, minus our 5y equals to 15. We can then subtract 10 from both sides. And that'll give us minus 5y on the left side equals 15 minus 10. That'll give us 5 on the right side. And then we can divide both sides by a negative 5. Here the y is now by itself. And that's equal to 5 divided by negative 5 is negative 1. So that's another solution. X equals 5 and y equals minus 1. 5 minus 1. Okay. Now, this is a linear equation, which means we know that the graph is made up of all the points on the same straight line as these 2 points fall. So I could come over here and I could graph that. Okay. Let's see here. That would be 3 comma negative 0. So that would be 3 comma negative 0. Negative 0, I just invented a new number. 0 comma negative 3, that would be 3 steps down from the origin. 0 comma negative 3. And 5 comma negative 1, that would be 5 steps to the right. And 1 step down. 5 comma negative 1. And now you can connect your dots and form your line. Note that this is the graph of a linear function. It's a straight line. You note that from what we saw a moment ago, we can also say that this is the graph of a function. Notice every vertical line crosses this graph no more than one time. Doesn't matter how hard you try, you can't find any vertical lines that cross more than once, like that. Okay? So this equation gave us a graph. That graph is made up of a collection of ordered pairs. Those ordered pairs form a function. Now that's a lot to say, right? Let me go ahead and write that down. Formally, what happened is the equation gave a collection of ordered pairs as solutions as seen on the graph. All right, we're able to find a bunch of solutions, and those ordered pairs are seen on the graph right here. Oh, I guess there should be a period here. That's a new thought. As seen on the graph, those ordered pairs are a function. You can see that from the vertical line test. Now, no one ever wants to say that, not once, let alone over and over again. But whenever we're dealing with equations, this is a possibility that that equation, whatever it is, might give us a set of solutions. And when you look at those solutions might form a function. So instead of saying all of this, generally the way we say it is the equation generates a function. You can't really say the equation is a function because an equation is not a function. A function is a set of ordered pairs. But the solutions to that equation are a function. Right? So instead of saying all of this stuff, we just abbreviate it by saying this generates a function. And that means the same as all of this other stuff does. Right? Now, if an equation generates a function, then that means that it is a deterministic relationship. That means that, as we saw before, a function tells you, once you know what x is, that automatically forms y. Well, if that's the relationship, wouldn't we be better off writing this equation in terms of x? Wouldn't we be better off writing it as y equals something? After all, that's what a function is. A function is, among other things, a deterministic relationship. It tells you, you tell me what x is, and I can automatically tell you what y is. Well, that's what equations look like. That's what equations mean when they look like y equals something. You give me that something, and I can figure out what y is. So, even though this equation generates a function, we oftentimes want to rewrite the equation so that it looks like y equals something, because that drives home the point that these aren't really two different variables. Rather, you have an x value that you can choose. Notice I did here, I chose x, and then that y is automatically determined by that choice. Notice, I told you what x was, and then we didn't have a choice. There was only one correct y value. I gave you an x, and once that was given, there's only one correct y value. But that's what we mean when we talk about a function. So, that's explicitly written. This is called function notation. Function notation is a way of rewriting an equation, not so that it changes the equation, not so that it means something different, but to highlight the fact that that particular equation generates a function. So here's how this works. I'm going to go ahead and take the exact same equation that we had just a moment ago, because we know that one generates a function. 2x minus 5y equals 15. Let me solve for y. You say, can I solve for x? No, because by definition, a function is going to have a deterministic relationship from the first entry to the second. Meaning, once I know what x is, I can figure out what y is. It doesn't work backwards. Notice, if I know x is equal to 1, I know y is equal to 5. If I know y is equal to 5, here I don't know what x is, but this is still a function. So, for any function, we can solve for y if we know what x is. We can't necessarily solve for x if we know what y is. All right, so we have to solve for y, the one we're looking for. So here we're going to say, okay, we're going to solve for y. Let's subtract 2x from both sides. 2x minus 2x is 0. That gives me just minus 5y equals minus 2x. That's a positive, so I'm going to say plus 15. And then I can divide everything by a negative 5. So far, all we're doing is we're isolating the y variable. So this gives us y equals a negative divided by a negative is a positive. 2 over 5x. A positive divided by a negative is a negative. 15 over 5 is the number 3. All right, so here what we've done is we have isolated our y. So let's label that. That's our first step. Isolate y. Okay. Now, this shows us, hey, you tell me what x is. I plug it in right here, and that tells you what y is. That's how functions work. You give me x, the function gives me y. But to highlight the fact that this is a function, or whether that this generates a function, to highlight the fact that y isn't a free choice, rather it's determined once you know what x is, we rewrite y in the following notation. We're still going to leave this the way it was. We're going to write this as 2/5 x minus 3, but instead of saying y and treating it as if it were a separate variable, which it's not, it depends on x, we're going to write this as f, and then in parentheses we're going to have the variable x. This is read as f of x. F stands for function. Now, we don't actually have to use the letter f. F is considered to be the name of this function. It's a label. Right? If you wanted to label it something different, you can. You can say g of x, h of x, y of x, p of x, q of x. Any letter will work. However, in most introductions to function notation, they use f because f is easy to remember, because f for function. But you can use any label you like. The way this is read is f of x is all that stuff. F of x is 2/5 x minus 3. What this does is it highlights the fact that there is no y variable on its own. It's x is a variable, but once we know what x is, that determines what this is going to be. The way function notation works is as follows. Let me keep using this example here. Let's say I have my function f of x is equal to 2/5 x minus 3. Okay, well, with a function, once I know what x is, that uniquely tells me what y is, and there's no other choice. There's only one correct answer. Okay? Well, let's say that I want x equals to 15, for example. Okay, well, the way I would ask it is, let's go ahead and find f of 15. This x can be replaced by any other value you like. It can be replaced with -6, positive 55, negative 1/3, it doesn't matter. This x is called the argument of the function. The argument of the function. And that argument represents the variable in your function. It represents the variable in this equation. So, what that means is, if I replace this variable of the equation with a number, that means this variable will also behave the same way. So here, we're going to find f of 15. F of 15 is that argument, that x gets replaced by a 15, which means over here, this x will also be replaced by a 15. Okay? So now we can go ahead and multiply. Remember, 15 is like saying 15 over 1. Okay? That's going to give us 15 times 2 is 30. 30 divided by 5 is 6. 6 minus 3 is 3. So there you go. F of 15 is 3. We could do that for any other number we like. Let's say we're going to find f of 0, for example. Well, then again, the argument gets replaced with the argument is 0 here, which means that x got replaced with a 0, which means this x should also be replaced by a 0. Whatever the argument is, that's what's telling you that's the value of your variable in your equation. Once the argument is replaced with a number, that's telling you that variable is getting replaced by that particular number. And now we simplify. Anything times 0 is 0, minus 3 is negative 3. I'll go ahead and give this a try. Go ahead and find f of, let's say, negative 10. And go ahead and find f of positive 4. Take a moment, pause the video, and go through those. Once you have a result, go ahead and unpause and we'll confirm that together. All right, here f of minus 10, this x is being replaced by that value there. So it's going to be 2/5 times negative 10 minus 3. All right, well, let's see here. 2/5 times negative 10, that's negative 4. Minus 3 is negative 7. And there we go. F of negative 10 is negative 7. Let's try f of positive 4. That's going to be 2/5 times 4 minus 3. Like that. 2/5 times 4 is going to be 8/5. And then if you take 8/5 and subtract 3, that's going to be what? Negative 7/5. And there we go. So here, that argument represents the value of the variable in your equation. So if that argument gets replaced with the number 4, that means the variable in your equation has the value of 4. And then you do the arithmetic to get your result. If you have a different function, that's fine. If ever you're dealing with different functions within the same within the same problem or even on the same page, it's often the convention to give them a different name. If you call every function on this page f, it makes things confusing because you say, okay, I want f of x. Which f? So if we're going to talk about a different function, generally we give it a different label. Here I'll just use the next letter of the alphabet. I'll go with G. This is read as g of x, and it works exactly the same way as f of x. It's just a different label. If I wanted to use a different letter, I could say h of x. That's fine. W of x. It doesn't matter. Any label's fine. The point is we want to have different labels for different equations. All right. So here I'm just going to make one up. Let's say g of x is equal to x squared minus 5x. Notice that in this equation we have more than one instance of that variable, and that's fine. It works the same way. We're going to say find g of, let's say, 6. Okay. Over here, because the argument represented the variable in your equation, when you replace that argument with a number, the variable gets replaced by that number. Here, the argument of your function represents the variables, more than one, of your equation. Well, actually, it's one variable, but it appears multiple times. But when you replace that variable with a number, then these instances of that variable also get replaced by the number. So if there's more than one variable, like that, if there's more than one x, then they all get replaced. So this will be 6 squared minus 5 times 6. Now notice it happened there for both of the x's. And now we simplify. 6 squared is 36, minus 6 times 5 is 30, and 36 minus 30 is going to give us 6. So go ahead and give that a try. Let's say you have, and I'll just use the next letter of the alphabet, I'll say h of x. H of x is 2x divided by, let's say, x plus 5. Okay, go ahead and find, let's see. Let's find h of negative 10. Go ahead and give that a try. Pause the video, and when you're done, go ahead and unpause and we'll go through it together. All right, so here, this x represents these x's. So if that x gets replaced by a negative 10, then these x's get replaced by a negative 10. Just like that. And now we simplify. Negative 10 times 2 is negative 20. Negative 10 plus 5, that's a negative 5. And then negative 20 divided by negative 5, that's a positive 4. So h of negative 10 must be 4. All right, so that is h of negative 10. Now, a graph is a useful way to talk about a function or to think about a function. You can tell if an equation generates a function by looking at its graph. However, you can get more than that information from a graph. You can evaluate functions through that graph. For example, here you see the graph of a function. What equation gave us this function? We're not going to worry about that. Just consider here's the graph of a function. It certainly is a function because after all, it does pass the vertical line test. Every vertical line you can think of crosses the graph no more than once. Notice over here, this vertical line doesn't cross at all, but that's okay, as long as it crosses no more than once. All right, now from this, you can see the ordered pairs. Right? You can see that if x is equal to 1, y is equal to 3. Here I used all whole numbers, so there's no fractions in here, so it doesn't look like this wouldn't be 2.9 or anything like that. If it looks like 3, it should be 3. Okay, so let's say from this graph we wanted to find something like what we just did. Well, for example, let's say this function that I have drawn here in orange, let's say that I'm going to call it the function, let's see, I've already used f, g, and h. Let's call this one w, because why not, right? Look, given the function y equals w of x in the graph, the one that you see on screen here, the orange one, let's go ahead and find the following. So let me go ahead and do the first one. I'm going to go and find w of 2. Well, what that means is, if my x value is 2, right, find w of x, the x is 2, well, what's the y value? Because after all, y is the w of x. So if I come over here, my x is 2, that means that my y, which means the same thing as my w of x, must be 8. Right here, if x is 2, y is 8. So here, w of 2 is y. That means on the graph, we can see that that's the number 8. If I find w of 1, same thing. I know my x value is 1. So my w of 1 must be the y value that I get when x is 1. Okay, well here's x is equal to 1, and so here y must equal to 3. So w of 1 is equal to 3. So go ahead and give that a try. Let's have you find, so go ahead and give this a try. Find w of 5, and go ahead and try find w of 6 is fine. Go ahead and pause the video. You're looking for w of 5 and w of 6. Let's go and blow that up so you can see it better. Go ahead and pause the video. You're looking for w of 5 and w of 6. Once you have those, go ahead and unpause and we'll confirm it together. All right, so let's take a look. If we're looking for w of 5, that means we're going to find what happens to our y value when x is equal to 5. Okay, so here x is equal to 5, and our y value is between 0 and 2. Oh, well, it's got to be the number 1 then. Right? I said here I'm using only whole numbers. There's no fractions. So when x is equal to 5, y is got to be 1. Okay, so then that means that w of 5 is equal to 1. Likewise, w of 6, when your x value is equal to 6, your y value is, if you follow that back, that's a value of 4. So w of 6 is equal to 4. When x is 6, y must be 4. Okay? So note that this isn't really any different than reading a graph normally is. Function notation doesn't change how things work. It changes how things are labeled. It changes how we refer to things. And later on, it actually serves as a good shortcut for a lot of other things. The reason we have function notation isn't just to make things more complicated or to randomly change things for no reason. The reason we have function notation is because things are going to be easier to refer to, easier to summarize, and easier to do with function notation rather than using the traditional language and equations that we talk about when we use equations. Right? But for now, we're just learning how to do this. The benefits of that will become more apparent as we start using them for things. All right, finally, the last thing. You note that before, when we saw examples of functions, some functions go on forever in both directions. The graphs go on forever in both directions. However, some stop after a certain time. They don't go on forever. They only exist on part of the plane. Well, why is that? Well, one reason that can happen is because the equation that generates that graph, the equation that generates that function, might not be defined everywhere. You say, what do you mean by that? Well, remember, not every operation can be done. For example, you can't divide by 0. Another example is, unless you're willing to deal with complex numbers, the square roots of negative numbers just don't happen, right? If you square a negative number, you get a positive number. If you square a positive number, you get a positive number. And so there aren't any real numbers that you can square to get a negative number. So if I'm asking for the square root of a negative, there aren't any real numbers that do that. So whenever we have an equation that generates a function, that equation, that function that's been generated, might have some limitations. This is called the domain of a function. At the very beginning of this section, we illustrated a function like this. I took all the x values and grouped them together, and I took all the y values and grouped them together. When you take all the x values and group them together, that's called the domain. The domain of a function is every x value, every first entry of the ordered pairs. This right here is the domain. Incidentally, if you take all the y values and group them together, that's called the range of a function. We don't really worry about the range right now. Right now we're talking about the domain. The conversation of range is best left to a different time. Right now we're talking about domain. Incidentally, note this is not a function, so here we don't generally talk about the domain and range. That's left specifically for functions. Okay, so if we're saying we want all the x values, what does that really mean? Well, that means I want to find every x value which I can plug into a function. Right? Here, the only x values that I have are 1, 2, 3, and 4. 1, 2, 3, and 4. If I tell you x is equal to 9, what is y? You tell me, I don't know. I have no idea because it's not part of this function. I can't plug in the number 9 because it isn't defined. So when we ask for the domain, we're asking for what are all the x values that can be plugged into a function. That sounds kind of intimidating until you realize there's not a lot of numbers that can't be plugged into things. In fact, there's really only 2 exceptions. Recall from previous lectures and from previous information that division by 0 is undefined. Oops, I forgot an E, undefined. There we go. And, as I mentioned a moment ago, if you square a negative number, you get a positive. If you square a positive, you get a positive. So, if you take the square root of 4, there's 2 possible answers. There's a positive square root and a negative square root. But what happens if I take the square root of negative 4? Well, I can't get any real number when I do that. Because after all, if I take this and take the square root, there is no real number that I can square to get a negative. Every number that I square always gives me a positive. So here there is no real answer to this. There's no real number that does this. So division by 0 is undefined. The square root of a negative number is undefined for real numbers. So that means that when I'm trying to find the domain, there's not a lot of stuff that I can't plug in. So instead of trying to find every number that can be plugged in, the easier thing to do is to find the few numbers that can't be. So how does that work? Well, for example, all of these are going to have the same directions. We're going to find the domain. The first example is find the domain of the function f of x equals 5 over x minus 7. Okay? All right. For the most part, I can plug in numbers here and get some answer. If I plug in the number 10, that's going to be 5 over 3. And that's fine. Maybe I don't like fractions, but I still got an answer. If I plug in x is equal to 50, that's going to be 5 over 43. And that's fine. If I plug in 0, 0 minus 7 is negative 7. 5 over negative 7 is a perfectly good answer. So here, most numbers that I plug in are going to give me some answer. Okay, well, what numbers can't I plug in? Well, the only numbers that I can't plug in are any that make division by 0 happen, or which make me need to take the square root of a negative number. Here, there is no square root anywhere in this problem, so I don't have to worry about this second case. But I do see some division. So what I'm trying to do is I'm trying to make sure that I don't plug in a number that has me dividing by 0. Okay, well, let's figure out what number does make that 0. What do I have to do to get x minus 7 to equal to 0? Well, I could add 7 to both sides. And that would give me x is equal to 7. This right here is the only number that is not in my domain, because it's the only number that if I plug it in right here, gives me 5 divided by 0. Any other number will make this positive or negative, a fraction, a whole number, a decimal. Those are all fine. But by plugging in 7, 7 minus 7 is 0, and division by 0 is undefined. So here, this must be excluded from my domain. So what that means is I'm going to have every real number is my domain except for 7. Here, the domain is every real number except 7. So every other number in the world can be plugged in, just not that one. Okay? Whenever we write a domain, it's going to be a little complicated if we actually start writing it out in words. We don't really write any answer out in words. We have a symbol for everything, don't we? So here, the way we write this symbolically is as follows. Imagine a number line. Number lines go on forever in both directions. So I'm going to use this symbol, the symbol for infinity. This tells me that it goes forever and it goes forever. Now here, it gets a little confusing if I use the same symbol on both sides. So here I'll put a little minus in front of it, and that tells me it's going forever in the negative direction. Here, without the negative, that's going forever in the positive direction. Okay, so my domain is every number. Oh, except for 7. Okay, so right here, I have a little hole that's 7. Like that. So I'm going to write this, but without writing the number line. When I have a curved parenthesis, that means that that number is not included as part of my expression, as part of my interval. So here, I can write it in words. The domain is every real number except 7, or I can write it in what's called interval notation. From left to right, I'm going to draw the number line, but without actually drawing the line, just the labels. So from negative infinity to 7, And I'm going to put parentheses around here because I'm not including the number 7 as part of my domain. If I wanted to include the number 7, I would put a square bracket. So here, parenthesis means not included. And it doesn't matter which way the parentheses are going. It's this way or this way. Either one's fine. Brackets, whether they're going this way or this way, means that the number is included. Here we're trying to exclude 7, so we use a round parenthesis. But it's not enough to just say from negative infinity to 7. We also want all the other stuff bigger than 7. 8, 9, 10, all that stuff. So here we want everything starting from 7 to infinity. Again, we use a round parenthesis to show the fact that 7 is not included, like that. And whenever you have an answer that has multiple pieces, we stick those together using this symbol. This is read as union. Union just means stick them all together to form one big answer. So this is our domain. It's every number on the number line from minus infinity to infinity, except for the number 7. Let's see that again. Let me go ahead and find the domain of g of x equals x minus 4 over x minus 9. All right. The numerator doesn't matter when we're talking about the domain. You can't divide by 0. If the numerator is 0, that's fine. No worries, no problem there. It's the denominator that can't be 0. Okay, so what does it take to make the denominator 0? Well, I could add 9 to both sides, and that will give me x equals to 9. So this must be excluded. So on the number line, it's the entire number line from minus infinity to infinity, except we're going to have a little hole. We're going to have to throw away the number 9. Okay, so that means we want everything from negative infinity up to 9. But again, we're excluding 9, not included. So we're going to use parentheses for that. Negative infinity up to 9. But then, that's not enough. We don't want to just go up to 9. We don't want to just say 5, 6, 7, 8. We want to go on the other side of 9 too. 10, 11, 12, 13, those are all fine. So we're going to say starting from 9, but again, not including it. We have the parenthesis, not including 9. Everything past that, out to infinity. And we're going to have the union symbol because whenever you have more than one piece to your answer like this, you stick them together and say, okay, no, these aren't two separate answers. This is the union. All together is one answer. And that's our domain. Okay. Square roots, you're going to have something similar. Let's go ahead and find the domain. Of h of x is equal to the square root of 2x minus 7. Okay. Once again, if you take the square root of a negative number, that's not going to be a real number. Okay. So let's find what it takes to make this negative. We're going to take 2x minus 7 is less than the number 0. If it's greater than 0, that's positive. If it's equal to 0, well, that's fine. 0 is not negative. We want it to be less than 0. All right, so let's see here. 2x minus 7 is less than 0. Okay, well, we can solve this the same way we solve an equation. We're saying less than instead of equals. Otherwise, it's the same way of solving. We're going to add the 7 to both sides of the equation, or in this case, the inequality. That's going to give me 2x by itself is less than 7. And then I'm going to divide both sides by 2. That'll give me x is equal to 7 halves. Oh, sorry, I keep saying equals. It should be less than 7 halves. You can say 3.5, you can say 3.5, but fractions are perfectly fine. Okay. All right, so remember, this is what needs to be excluded. Anything that makes the stuff under the radical negative, meaning less than 0, we're throwing that away. All right, so here's my number line. From negative infinity to infinity. Okay, now, 7 halves. Right here, 7 halves. I'm going to exclude everything less than that, which means all of this stuff over here, I'm throwing it away. Anything less than, I'm throwing that away. Notice, I'm not throwing away 7 halves, though. I want to exclude everything less than 7 halves. which means 7/2 itself, I'm going to keep that. So when you're including a number, you're going to use a square bracket. Right? Here, our domain threw away the number 7, so it's excluding it. But here, it doesn't throw it away. It keeps 7/2. So here, note, you still include 7/2. So because you're including it, you're going to use a square bracket for that one. Okay, so my domain is going to be everything from 7/2. Notice I don't care about anything less than that, so I don't start from negative infinity. Starting from 7/2, and there's a square bracket around that because it's included, all the way out to infinity. Around the infinity, we're going to put a round parenthesis. That's a convention, notational convention. No matter what's happening for the other numbers, infinities always have parentheses around them. The idea being you never get to infinity. Right? Infinity is always infinitely far away. No matter how big of a number you have, you never actually get to the end of the numbers. You never get to infinity. So round parenthesis because you're not actually including that because you're never going to get there. So this is our domain. Okay, let's see that again. Let's find the domain of, let's say p of x is equal to the square root of, let's say, 6 minus x. Okay, same thing. We want to find what makes this negative. That's what we're going to throw away. Everything else is our domain. So 6 minus x is less than 0. Let's figure out where that is. Right? We're trying to find where it's negative. That way we can throw it away. I'm trying to isolate x, and here I can just add x to both sides. This will give me 6 is less than x. And there we go. Now, this seems a little strange. We never write our answers this way. We never say 6 equals x, or 6 is less than x, or 6. We always start with the x. So here, let's flip this around. Now, be careful when you flip it around. 6 is less than x. If I want to put the x first, I'm flipping everything, and that includes this sign. If 6 is less than x, that's the same as saying x is greater than 6. It's like saying, my brother is younger than me. That means I am older than my brother. 6 is less than x. That means x is greater than 6. All right, so be careful with that. Okay, so remember, this is where we're excluding. So go ahead and consider the number line from negative infinity out to infinity. Here's the number 6. We're excluding everything less than that. So we throw all this away. Oh, I'm sorry. We're excluding everything greater than that. X is greater than 6. So let me draw that again. We're excluding everything greater than 6. So all of this gets thrown away. Notice we're not throwing away the number 6. So 6 is still included in our answer. So we're going to use a square bracket there. Notice the bracket's facing this way now because our answers go this way. Here the bracket faces that way because our answers are on this side. And so here, our domain is everything from negative infinity up to 6. Again, infinities have parentheses around them no matter what. But here the 6 is included, right? We threw away everything greater than 6, but we didn't throw away the 6. 6 is still part of our answer. Just like that. So, to wrap this up, go ahead and give this a try. Find the domains. Let's give you two functions. Let's say r of x is equal to 2x minus 1 over 2x minus 5. Go ahead and find the domain of that. And then let's say t of x is equal to the square root of 3 minus 2x. Give those both a try. Go ahead and pause the video and write your answer. When you write it this way, you're going to write it in, this right here is called interval notation. As opposed to writing it in words, you write it in symbols from negative infinity to 6, from 6 to infinity. That's called interval notation. So here are the directions. Find the domain and write in interval notation. And remember, the order matters. If you're going from negative infinity to 6, go from left to right. So the negative infinity would appear first. Up here, we went from 2/7 to infinity to the right. So here the infinity is on the right. So make sure that's in the correct order as well. It's not just to have the right. It's not enough to have the right numbers and the right symbols. The order also matters. So go ahead and pause the video, give that a try, and once you are done, go ahead and unpause and we'll go through it together. All right, so this first one, we're going to go ahead and take the denominator and find what makes it 0. All right, so we're going to exclude whatever makes 2x minus 5 equal to 0. We don't care about the numerator. Whatever happens to the numerator is fine. It's the denominator that can't be 0. All right, so we're going to add 5 to both sides. Okay. And then we're going to divide everything by 2. If you want to write 2.5, that works fine. But here I'll stick with 5/2. So that's it. That's the only number you're going to exclude. All right, so if you imagine your number line from minus infinity to infinity, there's only one number which we throw away. That's 5/2. Since that's excluded, we're going to go from negative infinity to 5/2. We're going to exclude that. Okay, so that's negative infinity to 5/2. And then, that's not enough. We also want everything bigger. We're only throwing away that one number. So anything bigger than that's fine. So again, we're not including 5/2, but we are going with every number further to the right, to infinity. And since there's more than one part to your answer, you stick that together using the union symbol. And that is your result. For this one, we're going to find everything that makes the radicand negative. And that's what we're going to exclude. All right, so let's exclude whatever makes 3 minus 2x less than 0. Here, let me go ahead and add the 2x over this way. Since it's a negative, I can add it and turn it to a positive. On the other side, like that. And now let me divide everything by 2. So that's going to be 3 over 2 is less than x. And again, that looks a little unusual. Usually we're seeing the x first. So we can rewrite this. If 3/2 is less than x, that's the same as saying x is greater than 3/2. Right? If I am younger than my brother, then my brother is older than I am. So you have that reversed. Or if you're okay reading it that way, that's fine too. Either one's okay. So let's go ahead and talk about what that looks like. On your number line, from negative infinity to infinity, we're going to find 3/2 right there. And we're going to exclude everything that's greater than 3/2. So everything to the right. Notice we did not exclude 3/2. That's still going to be part of our answer. So we're going to write from negative infinity up to 3/2. Infinities always have round parentheses around them no matter what. This one, notice we did not exclude it. Right? We excluded everything greater than that. This number itself is still part of your answer. So you're going to use a square bracket to show that it's included in your domain. And that's it. And that is it for the material. If anybody has any questions, comments, problems, please make a note of those and reach out. And as always, I hope everyone has a nice day.